Okay, let's dive into this. We're talking about these huge neural networks, right? The ones that write, code, analyze. They seem almost like magic sometimes.
They really do. But we know they're not perfect.
Definitely not. They make mistakes,
Right.
like making things up, hallucinating, we call it.
Right. Or reflecting biases from their training data. That's a big one.
And maybe the trickiest part, they get outdated. The moment the real world moves on from their training data, boom, factual errors creep in.
Absolutely. And these aren't like one-off problems.
Mhm.
Errors can pop up again and again sequentially as the model's used in the real world.
Yes, things change, yeah.
And finding the error is one thing, but fixing it, especially once it's deployed, that's the real headache.
Yeah, because the usual fix is, well, it's massive. You basically have to retrain the whole thing or at least do some serious fine-tuning.
And the costs are just staggering.
Yeah.
You mentioned the source material on Llama.
Over $2.4 million. And the carbon footprint, 1,000 tons of CO2. Just to fix maybe one or two things. You can't do that every win.
No way. It's totally impractical for ongoing fixes. And that's, why people started looking into model editing.
Making targeted changes without the full rebuild.
Exactly. But the specific challenge this research tackles, the one in your source material, is lifelong model editing.
Okay, lifelong, so not just one fix.
Not at all. Imagine a model out there interacting and errors just keep coming, one after another, sequentially, hundreds, maybe thousands over its lifetime,
And the challenge is fixing the new one.
without forgetting all the old fixes you already put in. And crucially, without messing up everything else the model was doing right in the first place.
That sounds incredibly difficult.
It is. And that's where the existing methods really, well, they struggle. You've got static editors, right? Built for maybe one fix or a small batch.
Yeah.
They weren't designed for this continuous stream. Try using them sequentially, and the sources show performance just falls off a cliff, like after only a handful of edits sometime.
A handful. Wow. So definitely not lifelong.
Not even close. Then you've got continual learning methods. They're meant for sequential stuff, but they tend to forget catastrophically.
Ah, the forgetting problem.
Exactly. They overfit to the new fix and just poof, forget the original training, forget the previous edits. Plus, a lot of these methods need extra stuff,
Like what?
like access to the original massive training data set or big batches of similar errors to learn from, or even like perfectly matched inputs with different desired outputs. Data you often just don't have when an error pops up in deployment.
Right. So this paper, it focuses on a much tougher, more realistic situation.
Totally. It assumes you see an error and you need to fix it right then.
Yeah.
Using only that single bad input and the single correct output you want for it. That's it.
No extra data, no big batches, just the error itself.
Precisely. And that's the problem Grace was designed to solve. Grace General Retrieval Adapters for Continual Editing.
Okay.
So this deep dive is really about unpacking how Grace actually manages this, this lifelong editing puzzle, how it works, and how well it did in their test based on your sources.
Sounds like a really important piece of the puzzle for making AI more reliable. Let's set the stage a bit more in part one. You mentioned those error types, hallucination, bias, factual decay. Why do those specifically make sequential editing so critical?
Well, think about the impact, right? An AI hallucinating medical info, or giving biased financial advice,
Yeah, dangerous.
or just being plain wrong about some major world event because its knowledge is stale. These aren't just like minor glitches. They affect safety, trust.
And factual decay is constant. The world keeps changing.
Exactly. So the model needs to be updated continuously as things change. You can't wait years for a multi-million-dollar retraining just to update basic facts.
Right, and the cost isn't just money and CO2, it's downtime. Taking a huge model offline for weeks, that's a massive disruption. You need something fast.
Fast and minimally invasive.
Yeah.
And since errors often show up one by one.
You need a method that handles that stream, that sequential arrival.
Yes. Without making you stop, collect everything, and do a giant batch update, it needs to be incremental.
And that specific setting, sequential, data scarce, that's where the other methods just couldn't keep up. Continual learning forgets.
Yeah, the catastrophic forgetting is brutal. It's like cramming for one exam and wiping your memory of everything else.
And the static editors, the ones that
What?
tweak parameters.
They weren't built for the long haul, for sequence after sequence. Without lots of data to guide them, applying them repeatedly just degrades everything. Performance tanks. The sources were really clear about that failure mode.
So Grace steps in, designed specifically for this one error, one correction scenario.
Exactly. build for that specific constraint.
Okay, let's get into the clever part then in part 2. How does Grace actually do it? What's the magic trick that lets it remember fixes without breaking everything else?
Well, the really fundamental idea is that Grace doesn't actually change the original model's weights at all.
Okay, that's huge. So it leaves the base model alone.
Completely. Instead, it adds these small, separate things called adapters. You slot one into a specific layer inside the main model.
Like putting a little specialist helper module within one stage of the model's thinking process.
That's a great way to put it. And this adapter, it holds the fixes, the edits, in what they call a codebook.
A codebook. Okay, what's in it?
A few key things. First, you have keys. These aren't just the input text. They're the model's internal state, the activations in that layer right before it messed up on a specific input.
Ah, so the key is like a snapshot of the model's internal, uh-oh, I'm about to make this specific mistake moment.
Exactly. It captures that problematic internal state. And each key is paired with a value.
Key and value. Got it.
The value is basically a learned instruction. When a key gets triggered because the model enters that same problematic state again, the value steps in and tweaks the layer's output to apply the correction. It's the fix itself.
Okay, keys identify the problem state, values apply the fix. Now, what about those epsilon balls, the deferral radii? That sounded important.
Absolutely crucial. This is how it generalizes, and importantly, avoids interfering where it shouldn't. Each key has a radius around it, an epsilon, defining a small zone or ball.
Okay.
When a new input comes into that layer, Grace calculates its internal representation, its state. Then it checks. Is this state close to any of the keys stored in the codebook?
Close meaning inside that key's epsilon ball?
Precisely. If the new input state falls inside the epsilon ball of a stored key, Grace says, aha, this looks like a situation I know how to fix. It activates that key and uses its associated value to modify the output. The fix gets applied.
But what if it's not close to any key?
That's the genius part. If the new input state is outside all the epsilon balls of all the stored keys, Grace does nothing.
It just stays out of the way.
Exactly. It defers completely back to the original untouched model weights. So for all the inputs the model already handles correctly, Grace doesn't interfere. It only jumps in when it recognizes a pattern it's specifically learned to correct.
That deferral mechanism sounds absolutely vital. So how does this codebook actually grow and change as you keep throwing new sequential errors at it over time?
Right. That's a codebook maintenance strategy.
Yeah.
It's key for the lifelong part. When a new error comes in that needs fixing.
Yeah.
First, it checks if the internal state for this new error is close to any existing keys, if it's far away from all of them, or the codebook's empty.
It adds a new one.
Yep. Creates a brand new key value pair for this specific error. Give the key an initial radius, they call it point it.
Okay. What if it is close to an existing key?
Then it looks at the fix needed for this new error. Is it the same fix as the one associated with that nearby key?
Ah, so similar problem, same solution needed.
Exactly. Yes, Grace, thanks. Okay, this is just another example of that same kind of mistake. So it expands the epsilon radius of the existing key to include this new input state.
Making that existing fix cover a slightly broader range of similar problems, it generalizes.
Precisely.
Right.
What if the new error is close to an existing key, but the fix needed is different?
Ooh, okay. Similar situation, but needs a conflicting answer now. That sounds tricky.
It is. You can't just expand the radius then, or you'd mess things up. So Grace splits the keys.
It splits them.
Yeah, it shrinks the radius of the original key, making it more specific, and then it adds a new separate key value pair for this new conflicting error, giving it its own smaller radius, usually based on the distance between the two. This keeps the conflicting fixes separate but targeted.
Wow, okay. So it intelligently expands for similar fixes and splits for conflicting ones. That really feels like the engine driving this whole lifelong learning thing. And the values, the actual corrections, how do they get learned or updated?
Just standard machine learning, really. Back propagation. If Grace uses a value, but the model's final output is still wrong compared to the target correction.
It calculates an error.
Yep, calculates a loss.
Yeah.
And that error signal flows back to update only the parameters of that specific value in the adapter. The original model waits. Still untouched.
Got it. Okay, so the benefits seem clear for the sequential problem. Edits without touching the base model, generalizes using the epsilon balls, avoids messing things up with deferral, and handles conflicts with the maintenance strategy. And it sounds way more parameter efficient than adding loads of parameters up front.
Exactly. It's really tailored for that tough, real-world deployment scenario.
Okay, that's the how. But did it actually work? Part 3 is where we get into the experiments. How did Grace stack up against other methods when they ran it through hundreds, even thousands of sequential edits?
Right, this is the moment of truth. They set up tests specifically for this scenario. Long sequences of edits, one after another, using only that single error input and the correct output each time. The real acid test.
And they used different pounds of tasks, right, to show it wasn't just good at one thing.
Yeah, 3 key areas representing common model problems.
Right.
1. Question answering. They used a T5 model, about 60 million parameters, edited it to fix factual mistakes from a dataset called ZSRE while making sure it still answered correctly on a different QA set, NQ.
So fix facts without breaking general QA ability.
Exactly. 2. Classification with label shift. This one's clever. Used a BERT model, 110 million parameters, classifying legal documents from SCOTUS data. But they simulated time-passing training on old data, editing with newer data where legal categories might have shifted.
Like how the meaning of civil rights might expand over decades.
Precisely. They actually simulated things like that, relabeling older cases under newer categories, tests if the model can adapt its understanding as concepts evolve.
Very cool. And the third?
Hallucination correction. This is on a big model. GPT-2XL, 1.5 billion parameters.
Yeah.
They use data designed to spot factual errors in generated biographies. The edit task was find a hallucinated sentence, replace it with the true fact from Wikipedia. And they did this 1,392 times sequentially.
Wow. Over 1,300 edits on a big generation model. That's a serious test. And they needed specific metrics to track performance after all those edits, right?
Absolutely. It's not just about the last edit. They tracked
Go on.
edit success.
Yeah.
Did it fix the specific error you just gave it?
Makes sense.
Test retention rate, TRR. Did it keep performing well on stuff it already knew? Crucial for not breaking the model.
Right.
Edit retention rate, ERR.
Yeah.
Did it remember the fixes for all the previous edits? That's the core lifelong metric.
Okay, remembering the past.
And for hallucination, accurate retention rate, ARR. Did it stay accurate on inputs it was already good at, even after all the editing?
All right, so how did Grace actually do, looking at Table 2 in the source?
It was a pretty clear win for Grace. It significantly beat the 7 alternatives across these tasks, especially on that crucial balance between TRR, keeping old knowledge, and ERR, remembering past edits.
How much better?
They reported the average of TRR and ER was like 19% better for Grace on the QA task and 9% better on classification compared to the next best, which is a pretty big jump in this context.
19%. That's substantial. It managed to hold on to both the original knowledge and the previous fixes much better.
Yeah. Grace consistently got high edit success. It fixed the new thing and high edit retention. It remembered the old fixes while doing much better at maintaining test retention and accurate retention.
What about the other methods, like simple fine-tuning?
Fine-tuning methods were okay at fixing the latest error, IES, but they completely tanked TRR and ARR. Classic overfitting. They just forgot everything else.
And the other specialized editing methods?
Things like MEND or ROAM, which might work well in other scenarios, really struggled here in this sequential low data setting. Without the extra data they sometimes rely on, their performance just degraded badly over the long sequence of edits.
Okay, what about the codebook size? Did Grace end up needing a huge memory bank?
That was actually one of the really cool findings. For the QA task with 1,000 edits, Grace only ended up needing 137 keys.
Only 137 for 1,000 edits. Wow.
And for the classification task, 375 edits resulted in 252 keys. It shows that the expansion mechanism really works. It groups similar errors together under one key. It's compressing the fixes, not just storing every single one.
It's generalizing the corrections needed.
Exactly. Now, for hallucination, it was different. 1,392 edits led to 1,341 keys.
Much closer to one-to-one. Why?
Because the fixes were unique sentences from Wikipedia. Less opportunity for multiple edits to require the exact same correction value. But it shows Grace can handle highly specific individual edits when necessary, even at that scale.
Makes sense. What about speed? Does adding this adapter slow things down?
That is the main trade-off, yeah. Inference time. Adding the adapter layer and doing that similarity search for keys does add a bit of overhead.
How much?
For the D5 model, they found inference was about 1.32 times slower on average compared to the unedited model. It depends on the codebook size, but the search is efficient, so it's more of a fixed increase rather than something that explodes. Still, it's a factor to consider.
Okay, so Grace wins on performance, generalization, efficiency, but takes a small hit on inference speed. Let's get into part 4, some deeper analysis. Did they look more closely at that generalization aspect?
They did. They used holdout inputs. variations of the edits Grace had seen, but phrased differently.
To see if it recognized the underlying issue.
Exactly. And Grace generally applied the correct fix to these unseen variations, confirming the epsilon balls weren't just memorizing, they were enabling real generalization.
And did it matter where in the model they put the adapter?
Yes, definitely. Putting it in the middle layers,
Yep.
block 4 for T5, seemed to be the sweet spot. It generalized better to those holdouts and needed fewer keys than putting it too early or too late in the model.
Interesting. Middle layers capture the right level of abstraction, maybe.
Seems like it. And that initial radius, finite, they found us a tuning knob, bigger pointed, encourages more generalization right away.
Right.
But it can sometimes be too general and accidentally interfere with inputs that were already correct, hurting the test retention rate a bit. So there's a balance to strike there. They also saw that codebook size tends to level off over time, suggesting the maintenance strategy works well.
And the parameter efficiency, just how efficient is it?
It's really quite lean. The extra memory per edit is small, and most of it is just storing the key, the internal state, which isn't learned. For T5, even with 500 edits stored, the codebook was only about 1.3% of the original model's parameters, and only a tiny fraction of that was actually learnable values. Much better than methods needing large parameter matrices up front.
That's impressive. And you mentioned the codebook is inspectable. That sounds useful.
Hugely useful, and a big differentiator. Because it's separate, you can actually look inside. See which past inputs led to which key, see what the value is doing. It gives you transparency. You can potentially trace why the model gave a certain output on a new input by seeing if it matched a key. You just don't get that when the edits are subtly baked into millions of weights.
Right. Okay, we mentioned the inference time limitation. Any other caveats from the paper?
Well, they mostly focused on single-layer edits. Applying this to multiple layers at once is future work. And while it scaled to thousands of edits, projecting that to, say, tens of thousands or continuous deployment might need more research on managing the codebook efficiently. Also, it's targeted. Fixing one fact doesn't magically fix related facts.
It's not performing reasoning, just applying specific learned corrections.
Exactly. Isolated edits.
Okay, so let's wrap this deep dive up. Based on this source material, what's the big takeaway? What did Grace really achieve here?
I think the core achievement is showing a practical, effective way to do lifelong model editing. Handling that sequential stream of errors, using only the error examples without exorbitant retraining costs, and crucially, without making the model forget past fixes or its original capabilities. That's the key breakthrough.
So it outperforms the alternatives in that tough setting, it generalizes, it's parameter efficient, and it's somewhat inspectable.
That sums it up pretty well. It's a really promising step towards making deployed AI much more maintainable.
So why does this matter to you, the listener? Well, this kind of research is paving the way for AI systems that can actually get better over time, based on real feedback, without needing a complete overhaul every few months.
Yeah, imagine systems, language models, classifiers, whatever, they can be continuously corrected, made safer, kept up to date, much more easily and cheaply than today. It makes the idea of truly adaptive, reliable AI much more realistic.
It really does. And it opens up some interesting thoughts to mull over, doesn't it?
Definitely. If we can selectively edit a model's behavior or knowledge like this, what possibilities does that create? Could we have AI that truly personalizes itself based on your specific corrections over time?
Or systems that maintain critical, up-to-the-minute factual accuracy automatically.
Exactly. And how does this ability to precisely edit AI change how we build these systems, how much we trust them, and how we interact with them day to day? Something to think about.
Absolutely. This has been The Deep Dive.
Until next time.